All right? There's one more example. All right, our last example for today would be a pipe like this. And then you feed dilute solution of one species in the solvent into a pipe, into a reactor. In the pipe, inner wall of the pipe is coated by a catalyst. So between Z equal to 0 to C equal to L, inner wall of this pipe is coated by the catalyst. Whenever you have A reaching the catalyst, the reaction will be converted A into B. So there is a reaction, but the reaction takes place on the surface only. That means this is heterogeneous reaction, not homogeneous reaction. After Z equal to L, there will be no further reaction. So, what do we have here? What kind of transport phenomena we have in this system? Do we have mass transfer? Yes. In which direction? Is there any mass transfer in Z? In Z direction, is there any mass transfer? Is there any flow? Yes, of course, whenever you have flow, mass will be flow, right? So there will be mass transfer in the direction of flow. So this is obvious that in this particular problem, convective transport of mass is not zero, because there is flow that you force it to flow. So in this particular problem, you will have convective mass transport in Z direction for sure. And then, do we have mass transport in R? Yes, because conversion of A into B makes the concentration of A around the surface to be low. Concentration of A in the center is higher, so therefore there will be concentration difference. Concentration difference would drive the mass transport in R direction. It will be dominating by diffusion, right? Because there is no obvious flow in R direction. There is no force flow in R direction. So in this case, diffusion is dominating in R. Do we have momentum transport? We do. In which direction? In momentum transport. R. Do we have VR? No. We have only VZ, right? But VC change in R direction. So we have Z momentum, and Z momentum is function of R. Z momentum is transferring in R direction. Okay? Z momentum is also transferring in Z direction, right? that right? Do we have z momentum transfer in z direction? Seems like a long time ago. No, we do not. Because as long as velocity is constant in z direction, there will be no acceleration. So there is no difference in velocity along z direction. In that case, there will be no momentum transfer in z direction. Okay. Is there any energy transport? For this particular case, no. Just to be fun, there will be no energy transport here. But if the reaction here is highly exothermic, and then the pipe is insulated, what would happen? As long as the temperature, as long as the pipe is insulated, that means energy cannot transfer anywhere else. Temperature at the wall is supposed to be higher than temperature at the center. In that case, you have temperature difference along R direction. There will be energy transport in R direction as well. Okay? And if I say that, okay, the reactant feed here at low temperature, it leaves at higher temperature. In that case, there will be energy transport along z direction as well. So everything is combined into one particular problem. Can you analyze that? I expect you to do so. Maybe you may not be able to solve everything for temperature profile, momentum profile, and so on, but you should be able to analyze this kind of problem. What do we have here? What kind of transport phenomena you have? Because this is very important. And I'm serious about this because whenever you graduate and you work in the plant, you need to be able to understand everything inside the plant. Otherwise, you cannot solve the problem. Okay? And understanding like this is much more important than solving the profile, because I don't think anybody here after graduation would turn back to solve energy profile again. All right? But understanding like this is very important. If you do not understand, you might solve the problem incorrectly and might cause the problem to get worse. Okay? All right, so in this particular problem, you have momentum transport and mass transport at the same time. And as usual, we will start somewhere. We will start with mass or momentum. Which one you should start first? If you want to start with momentum, you need to ask yourself whether or not you can assume density, viscosity to be constant. If you want to start with mass transport, you need to ask yourself, do you know velocity profile, right? Because right now we have convective transport dominating in z direction. In order to solve for mass transport along z direction, you will need to know velocity profile. So this is very obvious that you need to start with momentum. Okay? Starting with momentum, you should normally assume that viscosity and density at this particular moment would be constant. And the word constant here means constant with respect to position. The viscosity does not change much with respect to position. Okay? And the key here is dilute. The solution is dilute. That means the concentration of A and B along the Z or R direction does not change much. Majority of the solution will be solvent. So therefore, it is reasonable to assume that viscosity and density to be constant. And in this case, it would be roughly approximately the same as viscosity of pure solvent. Okay? Then you can set up equation of motion and equation of continuity for overall mass balance, and then you get velocity profile. And you should know by now, after several examples, that velocity profile here will be written as V maximum times 1 over R and R capital R. Right? I just want to emphasize that this equation here, or this velocity profile, was achieved from momentum transport under assumption that viscosity is constant. Then we can start using start doing mass transport problem. Again, when you start solving mass transport problem by using equation, there are two kinds of equations and two bases. You must choose first whether you want to use mass basis or molar basis. Which one should you use? Molar. Why? Because we have reaction here, right? Reaction here tells you that molar basis is better. So when you have molar basis, there's two more choices that you need to choose. There's one equation that is written in form of combined flux, Na. The other form of equation is written in form of velocity, V star. Which one should you use? In this particular case, since velocity is determined by momentum transport, and you can assume that the fluid moves with this velocity. Okay? So V is known. So it's better to use the equation of continuity in form of velocity. And this is the equation of continuity.